lesson. Okay, right. Now for A2, the first chapter that you will most probably learn is motion in a circle. Now, motion in a circle is actually kind of like a continuation of kinematics from AS. So in kinematics, you are interested to know when in kinematics AS, it was a study about motion. You were interested to know how far an object has moved, how fast did it move, and whether was it speeding up or slowing down. And then the type of motions that you were dealing with were pretty straightforward. It was either a straight line motion or either a parabolic motion. That was what you learned in AS kinematics. It is a study about motion, but most of the motion that you dealt with was mainly either straight line motion or curve motion, specifically parabolic motion. Now, motion in a circle in A2 is actually a continuation of kinematics. Just that in this chapter, you are specifically learning about motion in a circle. Okay, so you are specifically learning about motion in a circle. All right, wait, Kai Cheng has just joined in. Yeah, hi Kai Cheng, we just started a little, okay, I'm referring to the notes here. Okay, right, so circular motion, we are only going to, it's also a study about motion, but this time, yeah, no worries, Kai Cheng, all right. So motion in a circle is still study about motion, just that it is dealing specifically with an object that moves in a circle. Okay, so when something moves in a circle, we're also interested in describing how far has it moved, how fast was it moving, and also whether was it speeding up or slowing down. Okay, so the first page here will basically tell you about certain quantities, physical quantities that you need to know. Okay, first things first, let's just say that you have an object that is at position A, and then it moves all the way to position B, following the path of a circle, like the ones that you're seeing right over here. Now, when it moves like this, following the path of a circle, it will tend to make an angle at the center of the circle. So this angle that your object has made when it moves from point A to point B, angle, you learn that it can be measured in terms of degrees or radians. There are two different units for angle. So specifically in motion of a circle, when something moves and it covers a certain angle, we are normally interested to know the angle covered in terms of radians. Okay, so we define angle in radians as just the ratio of arc length to radius of circle. You may have seen this equation before, where we tell you angle in radians for a circle is actually the arc length as divided by your radius. Okay, so this one gives you angle in radians. This one is angle where the unit is radian. Okay, now this one is actually definition of your physical quantity. In A2 questions, you will normally notice that definition questions can be broadly divided into just two types. Either is definition of a physical quantity or definition of a unit. The first statement here is actually talking about definition of a physical quantity, which is angle in radians. Now, you will also sometimes be asked to define a unit. Okay, so in our case, if we ask you to define 1 radian, what is 1 radian? 1 radian is defined as the angle subtended at the center of a circle when the arc length is equal to the radius of the circle. Okay, so this one here, the second one, is actually defining for you the unit. Okay, so if you look at this original equation here, you can only get 1 radian if, say, this one is 1 meter, the arc length is 1 meter, and the radius is 1 meter. It's 1-to-1 ratio. So you say that 1 radian is when you have arc length equal to radius of a circle. Okay, right. Then after that, if you're talking about something that moves in a complete circle, just now I talked to you about the object moving from point A to point B. What about the case where it moves a full 360-degree circle like this? Now, for the case where something moves a full complete circle, where the radius is r and the arc length is s, the arc length would actually be equal to the circumference of the circle if you make one complete circle. So the arc length is actually 2 pi r. Now, it's because of this, where one full circle, the circumference is 2 pi r, that you can eventually deduce that 360 degrees is actually 2 pi radian. How do we do this? Is because you see, we know that angle in radians is arc length divided by radius, right? When you have a full complete circle of 360 degrees, your arc length is actually the circumference of your circle. Okay, it's 2 pi r. So 2 pi r divided by r, the r will cancel each other off, eventually giving you 2 pi radians. Okay, that's why we can say that 360 degrees is actually equivalent to 2 pi radians. Okay, so that is one thing to note. Now, there are also some questions, some rare questions sometimes where they will ask you to convert degrees to radians or radians to degree. So this one will be something you've learned in maths before. If you want to convert degree to radians, you multiply by pi over 180. If you want to convert from radians to degrees, you multiply by 180 divided by pi. Okay, so this one is what you will do. Now, moving on to some other physical quantities used to describe motions in a circle, you have something called angular displacement and angular velocity. Now, last time in kinematics, you learned these quantities before, specifically displacement, velocity, and acceleration. So in AS, you learn these three specific quantities and they had their own definition. Now in circular motion, you will see something similar to these quantities again, okay? But they're named differently, slightly differently, and they have different meanings to it, okay? The first one that you will encounter is something called angular displacement, given the symbol theta. And another one you encounter is angular velocity, which is given the symbol omega. Now this W, which looks curvy and fat, is actually your Greek symbol omega. Okay, it's actually your Greek symbol omega. Okay, it is usually used to represent angular velocity. Now, when you are talking about symbol omega, some of you may think that isn't omega this symbol? This one is also the Greek symbol for omega. Sorry, the Greek letter symbol, not Greek symbol. Greek letter symbol for omega. This one last time was used to represent resistance. Now, these two symbols are actually correct to say this is correct to say that these two symbols are the Greek letter omega. It's just that one of them is uppercase, one of them is lowercase. If I tell you the letter A got two types, right? Either is a capital A or small a, right? We call this uppercase A, this one lowercase a, right? So one of these is actually an uppercase omega, one of these is actually a lowercase omega. I don't remember which one was it, okay? But strictly speaking, those two are actually still omega. Just that one of them is uppercase, one of them is lowercase, okay? Now, back to the topic. Now, angular displacement tells you how much of an angle you have turned. It is formally described as angle turned through from a reference point in a specific direction, okay? So this is the formal definition of angular displacement. It describes to you how much angle have you covered. So same like your displacement definition from AS. In AS, we say that displacement is distance from a reference point in a specific direction, right? So you notice the similarity in their definition, just that they change certain terms to adapt to circular motion. Rather than saying is distance move or distance from a reference point, they say it's angle turn from a reference point in a specific direction. Okay, you still have the mention of reference point and specific direction here. Okay, Now, angular displacement is measured in SI units or radians. And then the next quantity you learn about is something called angular velocity. You can think of it as just simply telling you how much angle are you covering per second, much like the case of velocity. Velocity is telling you how fast you're moving, right? It tells you how many meters have you covered per second. Angular velocity is a similar concept. Rather than telling you how much distance have you covered per second, it tells you how much angle are you covering per second. Okay, so it's because of this we normally define it as angle turned through per unit time, measured in SI units of radians per second. It is also correct to define angular velocity as just rate of change of angular displacement, much like you did for velocity. Velocity last time you defined it as rate of change of displacement, but for angular velocity, omega, you are also correct to define it as rate of change of angular displacement. You just need to add the term angular. Now, for angular velocity, there's an equation that you can use to calculate angular velocity, which is given by this, where we tell you angular velocity is the angle turn divided by time taken. Okay. Both angular velocity and displacement are vector quantities because they have a certain associated direction. Because when we say something moves in a circle, you can clearly see that either they will move counterclockwise or clockwise. There are actually two different directions that you can consider. So they are vector quantities. Now, when something moves in a circle, we also have to consider something called linear speed, which is measured in meter per second. Now, linear speed can just be thought of as the instantaneous speed at a point, okay? So it is always tangent to the point. Here we define linear speed at any point in a circular path is always tangent to the point. It just means that if you have something that moves in a circle like this, if I'm considering certain points along its path, maybe say point A, point B, point C, or point D here, the instantaneous speed, or rather the linear speed at any of these points will always be tangent to that point itself. So for A, it was this. For B, it was this. For C, it will be this. For D, it will be this. Okay, the speed will always be tangent to that point that you're considering. So it's because of this, you can also say that linear speed is tangential velocity. Okay, now there's an equation that you will often use when you want to relate angular velocity and linear speed together. That one is V equals to R omega. Okay, the relation between linear speed and angular velocity is this equation. This one you use quite often. All right. Now, how do you get V equals to R omega? Is obtained from your equation V equals to S over theta. This one is say speed. Then this one is distance. And then this one is time, right? Now, when something moves in a circle, the distance is actually your arc length. So we know that in general, the definition of speed is distance over time. But for the case of something that moves in a circle, distance is actually your arc length. Okay, distance is actually your arc length. So just now, previously at the top of the page, it was mentioned to you that angle in radians is actually the arc length divided by your radius, right? So the arc length is your radius times your angle. So arc length is equals to r theta. If you sub this one inside here, you're going to get V equals to r theta over t. Now you try to isolate out theta over t here. Theta over t is actually omega. Okay, so since omega is theta over t, therefore V is r omega. So that's why we can say this, no? V is equals to r omega. Okay, so I think the derivation is something that you need to know. Okay, this derivation is something that is kind of required All right, although I never seen it being asked before, okay, but just know how it's derived lah. Okay, now for circular motion, there are also some other useful equations for you to know that are written on the boxes below here. If you look at the equation omega is equals to theta over t, this one is angular velocity, this one is angle in radians divided by time. Okay, so specifically, if you consider something that moves in one complete revolution, meaning to say I have something that starts from point A, it moves all the way back to point A itself. In one complete revolution here, if I ask you what is the angle covered for one complete revolution, it will actually be 2 pi radians. Okay, and then the time taken is actually your period. Period, you last time learned this as time taken for one complete cycle, right? Okay, time taken for one complete cycle. So when you have something that moves in one complete revolution, in terms of the angle covered is 2 pi radians. In terms of the time covered, it's actually equivalent to 1 period. So if I have omega equals to theta over t, this becomes 2 pi over t. All right. And also this one, I can further rearrange it to become 1 over t, where 1 over t is actually equals to frequency. So I get 2 pi f. That's why you're getting angular velocity equals to 2 pi over t equals to 2 pi f. So bear in mind that this t here is period, okay? Time taken to complete one full complete circle. So this is something that you will use quite often later on also. Okay, this is quite important. And then if let's just say I talk about another different equation where this time I have v is equals to s over t. This one is basically just telling you speed is distance over time. So if I have something again that moves in one complete circle like this, in terms of the distance that I cover, the distance I cover is the full circumference of your circle. So it's 2 pi r. Okay. So right now, if I use the equation v is s over t, the distance covered is 2 pi r. The time taken is again my period. I'm going to get this. And then this one, if I try to single it out, certain things out, 2 pi r over 1 over t, this one will become 2 pi rf, giving me this. Okay, so this one is also useful to know, but I'll say that this one is not as important as the first one. This first one is very important. You use it quite often. Okay, so please remember this one. Any equation that you see inside a yellow box is something that is required to be memorized. Okay, anything that isn't generally is not required. Okay, so this covers certain physical quantity terms that you need to know when it comes to describing circular motion. So now we go to something else, something new, something called centripetal acceleration as well as centripetal force. Wait, let me just... So I think I'll go through here. Okay, now there's another quantity called centripetal acceleration. Just now we covered circular. So just now we covered angular displacement as well as angular velocity. We covered displacement and velocity. Now we go through something called centripetal acceleration, which is another kind of acceleration. Now, first consider an object that is moving along a circular path with constant speed. Okay. When we say something moves in a circular path with constant speed, it basically means something like this. Let's just say this is my starting point, and then after that, I move one full complete circle like this. Them saying that you're moving along a circular path with constant speed basically means that your instantaneous velocity or your linear speed is always the same. Just like I mentioned to you, your instantaneous speed or linear speed is always going to be tangent to your point considered, right? So you see this blue color arrow here. If I tell you that I'm considering all these points where the ball is moving, the instantaneous speed or the linear speed at each of those points is indicated by this blue arrow, which is always tangent to the point itself. Okay, so when we say constant speed, it will mean something like this. If let's just say this one was at 10 meters per second, everything else at all the other points, the linear speed would remain the same. Okay, this is what we mean by something moving in a circular path with constant speed. The linear speed or the instantaneous speed remains the same throughout. Okay, now we would say that the speed is constant here because magnitude did not change. All right, if you recall from your AS last time, there's a difference between speed and velocity. Speed being scalar, you only need to consider magnitude. But velocity being a vector, you need to consider both magnitude as well as direction. So when something moves in a circular motion, it is correct to say that your speed is constant because the magnitude never changed. But when it comes to velocity, we cannot say that the velocity is constant because you notice that the direction of your velocity is continuously changing. You see, this is the direction of your velocity at the different points. So here, we cannot say the velocity is constant because direction is continuously changing. So velocity here is actually continuously changing in the first place. And because velocity is changing, we say that the object is accelerating. Again, this relates back to your AS, where we tell you that acceleration is rate of change of velocity. So as long as you have velocity change, you're going to have acceleration. So because we determine here velocity is changing, there definitely must be acceleration. Okay, the object is actually accelerating. But what is the direction of the acceleration here in the first place? So under kinematics last time, I didn't really teach you kinematics, but I'll just go through it a little for you. There is a relation between velocity and acceleration. The direction of your acceleration will actually determine how your velocity reacts or changes. What do I mean by that is, say I have a velocity acting like this. I give you 3 different cases. If say my acceleration is acting in the same direction as my velocity, you will speed up. But if my acceleration is acting opposite to my velocity, you will slow down. Now, in general, for both of these cases, direction remains unchanged. Okay. Now, what if you have an acceleration that is perpendicular to your velocity? Now, in this case here, you will actually have direction change, but no magnitude change for the velocity. Okay, so if you try to look back at the circular motion described here in the question right now, the magnitude never changed, right? It remained at 10 meters per second throughout, but the direction was changing. Okay, so it's because of that you can deduce that the acceleration must be acting perpendicular to the object's velocity or motion. That's the only way you can have your velocity changing direction, but without changing magnitude in the first place. So over here, your acceleration is actually always acting perpendicular to your velocity here. Okay, it is always acting perpendicular to your velocity. Okay, that is one thing to note here. Okay, now it's because your velocity, sorry, your acceleration is always acting perpendicular to your velocity, that your acceleration is always directed towards the center of the circle. You see, if I try to extrapolate the arrow for all of the acceleration indicated here, they all seem to come from the center, they all seem to be pointed towards the center of the circle. Okay, so that acceleration, while it's correct to say it's acting perpendicular to the object's velocity, it will also be correct to say that the acceleration is always directed towards the center of the circle. Okay, now this acceleration has a very special name to it. It's called centripetal acceleration. This centripetal acceleration continuously redirects your velocity direction, but without changing its magnitude. And this allows your object to move in a circle in the first place. So simply put, the key takeoff point here is just this. Any object that moves in a circle must have centripetal acceleration. Okay, anything that moves in a circle for sure must have centripetal acceleration. It is centripetal acceleration that allows something to move in a circle in the first place. Okay, so that is the thing that you just need to know from here. Yeah, as long as it moves in the circle, there is something called centripetal acceleration. It's the thing that causes the thing to move in a circle in the first place. Now, when it comes to calculating centripetal acceleration, there are two equations that you need to know. The first one is centripetal acceleration is your linear speed square divided by the radius of your circle. The second one is centripetal acceleration is the radius of your circle multiplied with your angular velocity square. Okay, so you need to know both of these equations. Now, how do you get the second equation here? It's because of the relation V equals to R omega that you learned before. If I tell you that AC is V squared over R, but at the same time, we know that V is R omega, you will get R omega squared divided by R squared omega squared divided by R will cancel off, the square will cancel off, giving you R omega squared. That's why we can say that AC is also R omega squared. Okay. Which one would you use? It depends on the question. If the question gives you linear speed, then you will use this. But if the question gives you angular velocity, then you will use the second one. Okay. It depends on what you're given inside your question eventually. All right. And then one last thing to note is this. Or why is AC equals to V squared over R? There is a derivation for it, but the derivation is not required inside your syllabus, so I didn't really bother to put that in. Okay, so you really just need to know that centripetal acceleration is V squared over R. There's a derivation for it. Usually your textbook will write that in, but since it's not required inside your syllabus, I actually just omitted it out. Okay. Right now, if you ask me how is it derived, I can't really derive it because I did not commit it to memory. Okay, but just know that it's V squared over R or R omega squared. If you want the derivation later on, I can probably find it out for you. Okay, right? Okay, now back to the other thing. All right. Okay, now since we have an acceleration in the first place, there must be a resultant force that causes the acceleration. This is something that you learn in dynamics AS, where you learn about Newton's second law. Remember, F net equals to ma. So that time it was mentioned that a resultant force can cause its acceleration. Rather, you must have resultant force to cause an acceleration in the first place because F net is equals to ma. So if you have acceleration, you must have net force. Okay. So since you already determined there's acceleration here, there must be a resultant force that causes that acceleration. Okay, the resultant force is known as your centripetal force. Now in your notes that you have, this one probably was written as centripetal acceleration. So it was a typo error there. I've actually corrected it to become false. So in your notes that you have right now, I think this one is written as centripetal acceleration. It's supposed to be centripetal force, okay? The corrected one will be in Google Drive now, okay? So if you want to get the corrected page, you can just take it off from Google Drive later, okay? Right? So this resultant force is known as centripetal force. And same like what we learned last time, it was mentioned that F net and A are always in the same direction, okay? Resultant force causes acceleration. That is what we know. That F net causes acceleration. This is the first fact that we know. And then the second fact that we need to know is that net force and acceleration are always in the same direction. Okay. So for the cases now, we determine that there is acceleration, there must be resultant force. The resultant force is centripetal force. And additionally, that force, the centripetal force, must always be acting in the same direction as your centripetal acceleration. So this means that your centripetal force must always be acting perpendicular to your velocity or always towards the center of your circle. That one is actually shown in the second diagram that you have here. The arrow that you're seeing here is all representing the centripetal force. It is always the same direction as your centripetal acceleration. That's why it's always directed towards the center of the circle also. And that's why it's also always perpendicular to your velocity. Okay. So these two things where we say that the force and acceleration is perpendicular to your velocity or is always directed towards the center of the circle, you will make use of this knowledge in another different chapter eventually under magnetic field. So at the very least, just understand why is it like that first, okay? Because the state and explain question in the other chapter will require you to know this. Okay, now, if we have centripetal force, what is the equation that represents centripetal force? So since we say that just now, the centripetal acceleration is caused by resultant force, if we use F net equals to ma, we can actually adapt this to circular motion where we say that centripetal force is equals to mass times centripetal acceleration. So just now we know that centripetal acceleration is either v squared over r or r omega squared. So you just sub this inside, you will eventually get Fc is mv squared over r or Fc is mr omega squared. You are basically just taking the mass multiplied with the centripetal acceleration to give you the expression for centripetal force. Okay, so this is the equations representing centripetal force. Now, one thing to note here also is that centripetal force is actually a resultant force. Okay, it doesn't exist by itself. It must be provided by an existing force, such as string tension, frictional force, gravitational force, magnetic force, and etc. What do we mean by that is something like this. If let's just say I give you a block, it is being pushed by one force that is worth say 10 Newton, and then it encounters a resistive force of say 5 Newton. My net force here is actually going to be my F applied minus my R. So you see this F net, the resultant force, only came about because of these two existing forces. If I didn't have my applied force and I don't have my resistive force here, there is no F net. Okay, so F net is something that only arises when there are some other existing forces. That's what this statement is actually trying to tell you. Okay, it doesn't exist by itself. It's actually provided by some other existing force. Okay, so that is what we mean by centripetal force being a resultant force. Something must be acting as the centripetal force. Okay, there is no specific force just called centripetal force. it is actually provided by some other force. Okay, you probably get a better idea of what this means after you go through some of the examples in the next few pages. All right, so let's go through some examples of circular motion. When something moves in a circle, there are actually only two cases. You either have something moving in a horizontal circle or something moving in a vertical circle. Okay, so the first example we go through today is for motion in a horizontal circle. So we first talk about a mass that is tied to a string. Okay, now we consider a mass that is tied to the end of string that is swung in a horizontal circle with constant speed. So this is a top view where a person is actually holding a string attached to a mass and then is trying to swing it, say, in this direction in a circle. So since this mass is moving in a circle, we know that there must be centripetal force that caused the object to move in a circle in the first place. If something moves in a circle, there is centripetal acceleration, correct? But at the same time, there must be centripetal force that causes it. Okay, so since this object is moving in a circle, there must be centripetal force here that caused the object to move in a circle. But what actually provided you the centripetal force? In the case that is described here, is actually the tension in your string that provided you with your centripetal force to make the ball follow a circular path. Okay, the tension in the string here was actually the thing that provided you your centripetal force. Okay, now if you keep swinging your mass in a circle, if you swing it too fast, you can imagine that eventually the string will snap. Okay, now in the case where the string suddenly snaps under tension, what happens then would be that the ball won't continue to move in a circle. Instead, it will continue to move in a straight line tangent to the circle at the point where it snaps. So if, say, the object was originally at this position, and then you swing it too fast or too hard, and then all the way to here, your string suddenly snaps, the mass here won't continue to move in a circle. Instead, you just move off tangent to the point where it snaps. Okay, that is what this statement here is trying to tell you. Okay, just know that whenever something breaks, that thing cannot move in a circle anymore. You just move in a straight line tangent. All right. Okay, now if you want to analyze the motion of this object that's moving in a circle right now, looking at it from the top view won't really give us much information. It will be much more useful to look at it from the side. Okay, let's just say right now we look at the circle, the object moving in a circle from the side. When we look at the object that is moving in a circle from the side, there are two different directions to consider. We need to consider the vertical direction as well as the horizontal direction. Just like your kinematics last time, when you have something that moves in a parabolic motion, like your projectile motion, you always consider the horizontal motion and vertical motion, right? So it's something similar here for circular motion. You have to consider the vertical and horizontal motion. Now, when you are swinging the stone so that it moves in a circle, it was mentioned just now earlier that your stone was moving in a horizontal circle. So when your object was moving in a horizontal circle, your stone actually did not move up or down during the motion. Its vertical position was actually maintained. So since it didn't move up or down, its vertical position remains the same, there's actually no vertical resultant force. So if I were to analyze the forces later, you will notice that there's no vertical force, no resultant vertical force, okay? But what if I consider the forces horizontally? Now, if I consider the forces horizontally later, you will find out that there's a resultant force that actually allows the stone to move in a circle, okay? So why am I saying these first two statements? You look at the side view of your stone tied to a mass. Just now it was mentioned that your stone is tied to a string, the string would exert a tension T onto your stone. Okay. Now this tension T can be resolved into two perpendicular components. You can resolve it in the horizontal direction like this, as well as the vertical direction like this. Okay. Now you notice that this one forms a zigzag. So if I have an angle theta here, there must be an angle theta here also. All right. So now from here, I can actually work out an expression for the tension components. The horizontal component, the blue arrow here, would actually be T sine theta. Whereas the vertical component, the green arrow here, because it's adjacent to my arrow, sorry, it's adjacent to my angle, it will actually be T cos theta. Now, the blue arrow, why do I say is sine, is mainly because if I were to shift it to this side to complete the triangle, you will notice that this is actually opposite to your angle, so it's sine. All right. But some people don't like this kind of reasoning. The easiest they do, the easiest thing they'll do is that they just see which component is adjacent to the angle first. So they see this component is adjacent to the angle is cos, the other component must therefore be sine. No? That's how they remember it. Okay, so it's up to you. But at the very least, just make sure you get the tension components correct. Okay, the vertical component is T cos theta. The horizontal component is T sine theta. Okay, now just now I mentioned to you that there are no resultant vertical force because the object did not move up and down. What's happening here is that your mass was moving in a horizontal circle like this. Okay, during the time that is moving in a horizontal circle, the stone never moved up and down. So no motion up and down, vertical position maintained, no resultant vertical force. This would mean then T cos theta must be balancing the weight. So you have T cos theta equals to mg. This is the first relation that you can see from here. Okay. But then after that, when you move on to the horizontal motion part, you will notice that T sine theta is the only force acting here. It doesn't seem to be balancing anything else. So this one here is actually your resultant force, which is actually acting as your centripetal force. Okay, this T sine theta is actually the force that is acting as your centripetal force right now to allow your mass to move in a circle. You see, this one is the center of your circle, isn't it? COC. This force is pointing towards the center of the circle. It's actually acting as your centripetal force right now to allow you to move in a circle. So if I use equation Fc equals to mv squared over r, my Fc is actually T sine theta. Then it's equals to mv squared over r. So this is the second relation that you know. Now, you want to simplify these relations that you found out. One of the things you can do is you will just take equation 2 divided by equation 1. You take equation 2 divided by equation 1, the t's will cancel. Sine theta divided by cos theta will give you tangent theta. And then mv squared over r divided by mg will give you v squared over rg. All right. So this one can be used to represent the object moving in a circle right now. Okay. Now you don't need to remember this equation. This is not required in your syllabus, but what you need to know is how you analyze the diagram to work out some sort of relation. It's more important for you to be able to analyze the situation vertically and horizontally in order to derive some sort of relation. That is the more important thing here. Don't memorize this final equation here because this is not the aim of the syllabus. The aim of the syllabus is to ensure that you at least know how to analyze any given circular motion questions. Okay, so this is one thing to note. Okay, another thing I should probably mention to you is this. You guys probably would have tried your hand before at tying a mass onto a string and then trying to swing it in a horizontal circle. One of the things that you might have noticed was that if you swing your mass faster, the string with the mass tends to go higher. Meaning you say, if let's just say my speed increases, the speed with which I swing the mass increases, my string would actually go higher and higher and higher, right? If my speed increases. So one thing to note here is that no matter how fast you swing your mass that's tied to the string will never ever be perfectly horizontal. Because what will happen is that when theta is 90 degrees, like the one that you're seeing right over here, you will notice that nothing will actually be balancing your weight. Just now the mass is tied to the string. The mass has its own weight W, and then you also have tension T inside the string, right? So if you consider the case where your string is perfectly horizontal like this, there's actually no force that is balancing your weight. So it won't maintain in a horizontal position, okay? There's no component of tension that is actually balancing the weight now. Just now previously, there's actually a component of tension that is actually balancing the weight. That was T cos theta. That allowed your mass to remain vertical, that allow your mass to remain in the same vertical position. But if you're considering the case where the string is perfectly horizontal, it just cannot happen because there's no component of tension balancing the weight. Okay, so the mass will actually just move down instead of maintaining the position vertically. All right, so this is just one thing for you to know. Okay, then after that, yeah, maybe I don't go to the second example first. I should probably go through one past year for you. Okay, you probably have the past years that I sent to you, I think 1 or 2 days ago. I sent to you two different past years. One of it is your normal topical past year from from June 2015 to November 21, 2021. That one is 62 pages. And then I also sent you another separate past year. This one I name it as circular motion supplementary questions. Now, one thing to note here for you guys is that motion in a circle very rarely comes out as a standalone question in your A2. It is often combined with another different chapter called gravitational field. That's why you see this one here is circular motion and gravitational field. Circular motion by itself very rarely comes out as a separate standalone question. It's often combined with another chapter, okay? But there are some exceptions where there are standalone questions. So this other worksheet that you have here, the supplementary questions, is actually the standalone circular motion questions that have come out over the years from November 2002 until now. The standalone questions don't usually come out. It's very rare. Okay, that's why you see there aren't that many questions in this worksheet. Okay, it's because standalone circular motion questions very rarely come out, but they do come out occasionally. And actually, the last time the standalone circular motion came out was actually in November 2021, quite recent. Okay, but it's not included inside here. This one we will discuss at some point once I go through motion in vertical circle. All right. Now, for now, I just need you guys to look at page 7 of the supplementary questions. This is November 14 P41. So we'll discuss this one since this one has some relation to what we just did. Okay, so we're talking about November 17 P41. Sorry. November 14 P41. Let me open up the question. Okay, so if we go through the question, this is what we have. Where is the question? It's on the, yeah, okay. This is the question. Now we go through the question. We have a large bowl that is made from part of a hollow sphere. Okay. A small spherical ball is placed inside the bowl and is given a horizontal speed. The ball now follows a horizontal circular path of constant radius as shown in the figure. So you actually have a small ball that is being made to move in a horizontal circle following this path here. Okay, is moving in a horizontal circle. Okay, so since it's moving in a horizontal circle, one of the first thing that comes to mind is that the ball actually doesn't move up and down vertically. There's actually no resultant force vertically. That's one thing to note here. Okay, now the next part of the question mentioned this. The forces acting on the ball are just its weight, W, and the normal reaction force R of the ball on the ball, as shown in the figure 2.2. Then the next thing they'll ask you, the next thing they mentioned was that the normal reaction force R is at the angle theta to the horizontal. Now, by resolving the reaction force R into two perpendicular components, show that the resultant force F acting on the ball is given by the expression W equals to F tangent theta. Okay, so they gave you a hint already. They mentioned to you right now, this reaction force R, there is an angle of theta to the horizontal, resolving into two perpendicular components and show that the resultant force F acting on the ball right now is actually equals to this. So let's look at this one. Your reaction force R is this. You resolve it into two perpendicular components. You will have one force like this, and then one force like this. So this blue arrow, the horizontal force, is adjacent to my angle theta, so it will be R cos theta. The green colored arrow, the vertical reaction force, is actually going to be R sine theta instead. Okay, if you already determine which one is cos, the other one will be sine. This is quite simple to determine. All right, so these are the forces being resolved already, and then now you need to analyze the motion horizontally and vertically, just like the case in the notes just now. Okay, usually in circular motion questions, when you see these kind of questions where something moves in a horizontal circle, you tend to have to analyze the motion horizontally and vertically. So as I mentioned to you just now, because your object was moving in a horizontal circle, there is no resultant force horizontally. So I can say that R sine theta is actually just equal to W. Okay, so this one, no resultant force vertically. Okay, the resultant force is the only resultant force. If there's no resultant force vertically, that means the only resultant force is from the horizontal forces. Okay, so since we already determined that there's no resultant force vertically, if we have any resultant force, it will be from the horizontal forces. Okay, so just now we had the first relation, no resultant force vertically, R sine theta is equals to W. The next thing we will analyze is the horizontal component. So since the resultant force is just from the horizontal forces, if you look at the diagram for the horizontal forces, there are no other forces horizontally other than this only, other than R cos theta. So this R cos theta is actually the resultant force F. Okay, that's why here we can make a relation. F is actually R cos theta. this is saying that r cos theta is the resultant force F. Okay. Then this is our second relation. So we want to simplify the equation even more. What we'll do is that we will take equation 2 divided by equation 1. No, sorry, not 2 divided by 1. We take 1 divided by 2. We're trying to get rid of the trigo here. We're trying to simplify the sine and cos here into one single function. So it'll be easier to take sine divided by cos. So equation 1 divided by equation 2 will give you tangent theta. The r will cancel off. W will divide by f, giving you this. And then after that, you will notice if you rearrange them, you are going to get W equals to F tangent theta. So it's shown. All right. Okay, so this one should be all right. This one is worth 2 marks. Okay, then the next part of the question will ask you this. What is the significance of the resultant force F for the motion of the ball in the bowl? State the significance of force F or the significance of the resultant force for the motion of the ball in the bowl. So this resultant force here actually provides the centripetal force for object to move in a circle. Okay, so it was moving in a horizontal circle like this. You see, your center of circle is somewhere here. This one is directed towards the center of the circle. Is actually your centripetal force. This resultant force is actually your centripetal force. Okay, so it will be sufficient to say that it actually provides you your centripetal force to allow your object to move in a circle. So they just want one simple statement. It's actually providing your centripetal force. Okay, so that one is okay. Then after that, I'll just close everything here. Okay, the next part of the question mentions this. The ball moves in a circular path of radius 14 centimeter. For this radius, the angle is 28 degrees. Calculate the speed of the ball. So you make use of what you just did. You have to make use of the relation you just derived to find out the speed. Okay. Now, since this one is talking about something that moves in a circle, the two equations that you most commonly use is this. Centripetal force is mv squared over r, or centripetal force is mr omega squared. Just like I mentioned to you, which one you would normally use actually depends on what is given inside your question. So you read your question, they are asking you for speed, and then you double check the units. They are asking for the speed in meter per second. So if they're asking for something where the speed is in meter per second, it means this one is not what you want to use, because this v here is in, sorry, my mistake. Because your speed is in meter per second, this first equation here is what you want to use, because this v is in meter per second. What you will not use is the second one. You won't use this because this omega here, angular velocity, is in radians per second. Okay, that's what I meant just now when I mentioned, although there are two different equations, which one would you use depends on what is given inside your question. Here the one speed in meter per second, so you're using the first one. You will not use the second one because the second one gives you radians per second, right? So you will use Fc equals to mv squared over r, and just now we already determined that the F provides you your centripetal force. So it's F equals to mv squared over r. That's why I wrote it here like this. And then further to that, just now we also know that F tangent theta is equals to W. This was the relation that we derived in the first page. Okay, so you find out what is F from there. Okay, F is actually going to be W over tangent theta. That's why we can sub it as this. Okay, so you have everything here. Try to simplify it further. We do not know the mass of the ball, but that's fine because the masses will cancel each other off. So whatever is remaining, we know the values. So just sub everything in, you'll be able to get the value for V, the speed, the linear speed. So G over tangent theta equals to V squared over R is 9.81 over tangent 28 equals to V squared over 0.14. 0.14 is because 14 centimeter change to meter. Eventually we get V equals to 1.61 meter per second. Okay, right? So that one is fine. Okay, so this one is one question on circular motion. Then we move back to the notes, going to some other circle, horizontal circle cases. All right, so if you move back to the notes under page 4, there are also other different cases where something moves in a horizontal circle. The first example we did was for a mass that is being swung in a horizontal circle when it's tied to a string. Now, there are also other things that can move in a horizontal circle. For example, when an aircraft is flying. Now, when an aircraft is flying, say we have an aircraft that looks like this right now. Let's just say that this is the top view of the aircraft. And then say your aircraft wants to go to this spot here. If your aircraft was originally flying in this direction, in order for you to move to this spot, it will have to turn to move to this position, right? So usually when it turns, it may turn like this. Okay, it curves like this. So when it tends to curve or turn like this one here is actually part of part of a circle. Okay, the motion is part of a circle. This motion is part of a circle. It doesn't move a full circle, it moves part of a circle. All right, but for all manners and purposes, we still consider this as circular motion for the green highlighted portion. So since this green highlighted portion is moving in a circle, we also know that when it tries to turn to go to this spot here, it therefore must have centripetal force that's directed towards the center of the circle that allows it to move in a circle in the first place. Okay, now when an aircraft is trying to turn in the air, when it's trying to make a circle in the air, one thing to note is that the aircraft must actually bank, okay, in order to move in a circle. Now, what is banking of an aircraft? Banking just simply means something like this. You are actually rolling to one side. The aircraft rolls to one side. It tilts to one side now. In other words, what do I mean by that is, let's just say if I look at the aircraft from here, the front view, I tell you that, say maybe this one is the front view of the aircraft before banking, it will generally look like this, where your wings are straight. Okay, notice that here your wings are straight. But when it starts to bank during the part where it wants to move in a circle, it will now look like this. Your wings are tilted towards one side. It's actually rolling to one side. So this is the same aircraft, but banking. Okay, this is the front view, but during banking. All right, so you notice that your wings are tilted right now, and they are at a certain angle. Now, it is important to note that when your aircraft is flying, your wings will generate lift. Okay, the reason why your aircraft can fly is because the wings are generating lift to lift your aircraft up. And your lift is always perpendicular to your wingspan. So for the aircraft that is actually flying, you have the weight W acting downwards, but you also have the lift force that is generated by the wings. It will always be perpendicular to your wings. The lift force is always perpendicular to the wingspan. Okay, it's always perpendicular to your wing. All right. So if you're talking about the aircraft right now, if you consider the forces for the weight and the lift force, if your aircraft is trying to move in a circle, let's just say I tell you that the center of my circle is right over here. If you just look at the aircraft as it is right now, there is only vertical forces. There are no forces pointing towards the center of the circle to allow me to move in a circle. Just like I mentioned to you, if you have something that wants to move in a circle, you need to have centripetal acceleration, you need to have centripetal force. Centripetal force must come from some other existing force in the first place. So if you consider the case where the aircraft does not bank, the wings are perfectly horizontal like the ones that you're seeing at the front view, there are actually no forces pointing towards the center of the circle. No forces pointing towards the center of the circle means there is no centripetal force. So your aircraft cannot move in a circle in the first place. Okay, that's what the first two statements here are actually trying to tell you. A flying plane makes a turn in the air, it must bank to do so. If the plane does not bank at all where theta is 0 degrees, there's actually nothing that provides you your centripetal force. So your aircraft must bank in order to move in a circle. Why do we say this? Is because just now I mentioned to you that your lift will always be perpendicular to your wings, right? So if your lift is perpendicular to your wings, the moment your aircraft banks, your lift force can actually be resolved into two perpendicular components. A vertical component like this one, and a horizontal component like this one. Okay, so when it banks, it will tend to make a certain angle. Let's just say we consider the angle that it makes to the vertical. So the blue colored arrow, the vertical lift force, will be actually L cos theta because it's adjacent to your angle theta. The other component would therefore be L sine theta. So if I'm trying to move in a circle and I tell you that this is the center of my circle, I actually now have something that acts as my centripetal force. In my case, it's actually L sine theta. L sine theta is actually helping me to provide the centripetal force so that I can move in a circle. All right, that's the reason why your aircraft needs to bank right now so that you can have a force that acts as your centripetal force. If you don't bank, there's no centripetal force. So in your case, your aircraft must bank in the first place. Okay. Now, same thing as before, for the aircraft, we want to analyze the horizontal and vertical motion. Now, ideally, when your aircraft is banking, the aircraft will not fall down from the sky and it won't suddenly go up, isn't it? It by right ideally should maintain its vertical position, just like the mast tied to the string just now. So in the case where we try to consider the forces vertically, we can actually say that the weight W of the aircraft will be balanced by L cos theta. That's why L cos theta equals to mg here. This diagram here is actually this diagram here. Okay, it's the same thing, right? So vertically, no vertical motion, L cos theta will be equals to mg. But then now when we consider the forces horizontally, we know that this L sine theta is actually acting as my centripetal force. So L sine theta is actually mv squared over R. All right. Now I want to simplify this relation. I can take equation 2 divided by equation 1 because I want to get rid of sine and cos. I want to make them the single function. So equation 2 divided by equation 1, L will cancel, Sine theta, cos theta will give me tangent theta, mv square over r over mg will give me v square over rg. So this relation here applies to the banking aircraft right now. Okay, so same thing as before, no need to remember this, but please be aware how to analyze the forces and how to derive some other resulting expression. This is the more important one. Okay, so this is banking of an aircraft. And then another thing I should probably mention to you is this. Now, when an aircraft is banking, your aircraft actually needs to increase its speed. So that its lift force L also increases. Now, before your aircraft was banking, before you made the aircraft bank, the lift force was equal opposite to W so that the plane does not fall. Meaning to say, if you look at this diagram right now, if I tell you that my weight was 1,000 Newton, the lift force must also be 1,000 Newton in order for your aircraft not to fall out from the sky. But now you consider this, if your aircraft banks, but without increasing its speed in the first place, look at what happens to L cos theta. Say my weight now remains the same as 1,000 Newton, but my angle now is, say, for the sake of discussion, is 60 degrees. Let me just erase this. Let's just say that my angle theta that I have is 60 degrees and my lift force remains at 1,000 Newton as before. My lift force remains at 1,000 Newton. So what happens to L cos theta? L cos theta would now be 1,000 cos 60. You actually have 500 Newton only. Okay, so previously, just now, you have L balancing the weight. They are equal opposite, so your aircraft did not fall off from the sky. But now, L cos theta is supposed to be balancing the weight, but the values are not equal. L cos theta is actually less than the weight. So therefore, the plane will fall. Okay, so here I actually already wrote it here. If the plane banks without increasing its speed, L cos theta is now less than weight W, so the plane will drop. Okay, but it's still able to move in a circle because you still have the L sine theta here acting as your centripetal force. It's moving in a circle, but it's dropping off from the sky, which is not something you want. You want to maintain your position in the sky while moving in the circle, right? So one way of doing that was to increase its speed. Okay, so just now I mentioned to you that lift force is always perpendicular to the wingspan. Another thing to note here is also this: the faster the aircraft moves, the larger the lift force generated. Okay, so that's the reason why we have to increase our speed in the first place, so that our lift force increases. So if we fly faster, we have a larger lift force. So by having a larger lift force, it could come to a case where now L cos theta is larger so that it can balance W. So let's just say, for example, if I say that my aircraft flies faster right now, if it flies faster, it could be that my lift force is now 2,000 Newton if it was flying faster. So now, if it is now 2,000 Newton at the same angle of 60 degrees, my L cos theta would now be 2,000 cos 60, giving me 1,000 Newton. So this time, 1,000 Newton is balancing exactly 1,000 Newton of weight. So my aircraft doesn't fall. Okay, so that is the idea here. If you fly faster, you have larger lift. Then after that, you could have a case where it can balance the weight. Additional question, how does an increase in speed generate increase in lift force? This one is something that you guys learn in SPM or IGCSE, I believe. An aircraft wing generally looks like this. This is what we call an aerofoil shape. So what happens here is that when your aircraft tries to move in this direction, airflow will go in this direction. Okay, so when air goes in the opposite direction and it hits your aerofoil, it will split out like this at the top and it will split out like this at the bottom. So what we'll tell you is that for the airflow below the wings, the speed is less, the pressure is high. But for the airflow above the wings, the speed is high, the pressure is low. So what will actually happen is that there's a difference in pressure causing a net upward force. Something like upthrust that you learned last time. When you learn upthrust, you remember there's a difference in pressure between the top and bottom surface, which in turn causes some sort of resultant upward force, which we know as upthrust. It is something similar for aerofoil also, for wing. So the general idea here was that if your aircraft moves, you would have airflow passing through your aircraft wing. The aircraft wing is specially shaped in this manner, which we call an aerofoil shape. It allows the airflow to move above and below the wing. So what we'll tell you is that the airflow above the wing will tend to move faster than the one below it. So when it moves faster than the one below it, it tends to create an area of low pressure. But for the airflow below the wings, it tends to move slower, so the pressure is generally higher than that of the top. So now between the top and bottom surface, we now actually have a difference in pressure, which in turn cause a difference in force, which is generally outwards. This is our lift force. So when you move faster, you're actually causing the difference in pressure to increase. So the difference in pressure increases, you will have a larger lift force generated. That is the idea behind it. Okay, you're asking me why increase in speed increases lift force, right? It's because it causes an increase in the difference in pressure between the top and bottom wing. So you have increase in force. All right. Okay, so this one is okay. This is for banking of an aircraft. Why does your aircraft need to bank when flying? So I'll just clear this one off. Okay, then the next thing would be on another separate thing that is trying to move in a circle. So the next example, this one I'll probably just go through this last example here. The first one, the previous example, we were talking about an aircraft that was moving in a circle. We now move to something that is more relevant that we can see every day. The example we're going through now, is for a vehicle rounding a bend on a horizontal road. So this one is something that you can easily appreciate. So if I have a car that was moving in this direction, when it's moving on the road, most roads that you see are not perfectly straight, right? They tend to bend towards the left or towards the right, isn't it? So when you try to follow the road, which bends towards the left or right, it could be that maybe for your current car, you're moving like this, following the curvature of the road. So when you're moving like this, when you're turning towards the left, you're bending towards the left, you are against moving partially in a circle. Okay, so this one is actually part of a circular path. So for this portion, the pink color portion, you're actually moving partially in circular motion. Okay, so for this part, since you're moving partially in circular motion, you again have centripetal force to consider. It is the thing that allows you to move in a circle in the first place. So now what is actually providing you your centripetal force? Say this one is the center of your circle. What is now providing you your centripetal force to allow you to move in a circle? The thing that allows you to move in a circle right now is actually your sideways frictional force. It is providing you your centripetal force right now. Okay. Now, your sideways frictional force is something like this. This one is your sideways frictional force. Now, in general, it's correct to say this. Now, if I look at the car from the side, this one is say top view. Okay. If I look at the car from the side, this is say the side view. You will be thinking, oh, if my car is moving like this, say this one is my motion. Isn't my friction supposed to be in this direction, opposing my motion? Yes, you are correct in saying that. So in the case here, my car is moving forwards. There should by right be friction opposing its motion. But at the same time, there's also a component of the friction that is acting sideways, which is this one. Okay, this sideways friction is actually acting as your centripetal force right now that allows you to move in a circle. Okay, so in this case, it is not lift force, it's not string tension that provided you your centripetal force, it is actually your sideways frictional force. Okay, so if you consider the motion vertically right now, there's no motion vertically, so reaction force is actually equals to the weight. You have vertical equilibrium here, nothing here to consider. But for the case horizontally, you're moving in a circle, your sideways frictional force will be mv squared over r, okay? Because Fc equals to mv squared over r. Fc is provided by your sideways frictional force, okay? So this one is something that you need to know. Now, it's also correct to say Fc is mr omega square, so that Ff is equals to mr omega square. You notice that I keep using mv square over r, right? It's also correct to use mr omega square, okay? It's just that I don't use this often. I often use this one, okay? So it's correct to write it in two different forms if you want to, all right? Okay, now one thing to note is this. When your car, just now for the case of the aircraft, I mentioned that when it turns, you ideally want to increase your speed, isn't it? So that you don't fall off from the sky. But now for the case of a car or vehicle on the ground, when you turn, intuitively you don't speed up, right? Because you know what will happen if you speed up too much, right? If you speed up too much, what will happen is that you will lose control of your car. And at the point where you lose control of your car, you will just move off straight, right? So the part where you move off straight is actually you moving at a tangent to the circle, all right? So under what cases do you actually lose control of your car? Under what cases can you not complete a circle? Why is it that usually when we drive and we turn, make a turning, we have to slow down? We know that if we go too fast, we will lose control of the car and then our car will just fly straight off somewhere, right? So why is it like that? Why is it that when we move too fast, we cannot complete a circle? So the statements, the last few statements here will actually explain to you why. Now, you need to first understand this. When your vehicle moves faster, you will actually require a larger centripetal force. Because you can see from here, Fc is equals to mv squared over r. If you try to move faster, your Fc required will also be larger. But here, for the case of a car moving around a bend or moving in a circle right now, your centripetal force is actually provided by your frictional force. And your frictional force has a limit to it. There's a maximum to the centripetal, there's a maximum to the frictional force that is acting as your centripetal force right now, that's providing your centripetal force right now. If it so happens that the centripetal force required exceeds the maximum frictional force available, the vehicle will actually not be able to move in a circle and you just move off straight along a tangent. So to illustrate to you with some values, let's just say, for example, my max friction is 1000 Newton. And then I move with a speed of, say, 30 meter per second. My centripetal force required is, say, maybe now 800 Newton. So in this case here, my FC is still less than the max friction. You can still move in a circle. Your FC is less, maybe I use a different color, sorry. Here I can say that your FC is still less than your max friction. So you can still move in a circle. All right. So you moving at this speed, your frictional force can still act as your centripetal force. There's enough of it available to act as your centripetal force. So you can still move in a circle. But what if, say, you speed up? Okay, let's just say you speed up. So you speed up too much. What then happens? Your maximum frictional force remains the same. Okay, your maximum frictional force remains the same as before. But now your speed is larger. Say maybe you try to move at 75 meter per second. So now your centripetal force required becomes a lot larger for you to move at that speed. Maybe now it is at 2500 Newton. So you know that your frictional force is the one providing your centripetal force right now. But then right now, the centripetal force required is just too much. Your friction can only provide 1000, but your required centripetal force is 2500. So in your case here, your FC is more than your max friction. So therefore, you cannot move in a circle anymore. Instead, you move off along a straight line tangent, which is this one here. Okay. When your centripetal force requires more than what the friction can provide, you cannot move in a circle anymore. You instead start to move off along a straight line tangent, which is this one. Okay, so this is what you can say. Okay, this one moves off along a straight line tangent. Okay, so that's why we cannot move too fast. If you move too fast, you come to a point that friction cannot provide you your centripetal force anymore. So you start to lose control of your car, and your car will just move straight off and fly off somewhere. Okay, right? So basically, there's one part here.